Acid and bases, when you put them together, we're going to, again, focus on the math part of it this year. We're looking for where the two solutions, where their mole amount is equal. So last year, you would have probably tested a bunch of indicators to see which is an acid and which is a base. So you can see that if you're looking for a neutral pH, this one is really the best. I like this one. This is the one we would have used if we were able to do a lab. Bromothymol blue. But you can see here, you probably tested phenolphthalein, litmus paper, the different pH papers. There's lots of tests you can do. Okay, so neutralization is when the moles of protons donated by the acid is equal to the moles of protons accepted by the base. So we do need to be careful of Stoich. So if you have a perfectly strong acid added to a perfectly strong base, then you get a nice neutral salt like sodium chloride and water to give a pH of 7. But if it's not a strong and weak if one of the substances is weak, then things can get a little bit hairy. So we'll deal more with that in grade 12. So this year we're just going to look at calculating when the moles of protons donated by the acid are equal to the moles of protons accepted by the base. And the procedure, the lab procedure to do this is called titration. So if we were in class, we would have used a burette. Which is over here. You can see this burette. And a burette has very, very precise calibration. And what that means is, though, they cost $92. So sometimes students are like, oh, Ms. Todd, that's all I remember from grade 11, which is hilarious, right? Of course. But anyways, and this procedure of titrating a solution is usually used to determine the concentration of something. So you could have to do a lab in university where it doesn't even matter what, like it's not about acids and bases. You need a solution for some other experiment, but you need to know the concentration of the solution. And the most quantitative way to do that is using really precise apparatus like a burette. So there's a burette. I tried to get this simple diagram here. This is a retort stand, and you use a special clamp to clamp the burette onto the retort stand, and then a flask contains a solution with an indicator. So it doesn't matter if you put an acid in the flask or acid in the burette or vice versa. It doesn't matter. It's just opposite. So if you have, in this case, they've chosen acid in the flask and base in the burette. If it was the other way around, then you would put base in the flask and acid in the burette, but it doesn't really matter. So then you're trying to find equivalence point, where the point in a titration when the number of moles of added solution is stoichiometrically equal to the number of moles of standard solution. So you, depending on what labs you did in grade 10, you might have just used the indicator like bromothymol blue to visually determine this. Mathematically, we want to know when the moles of acid are equal to the moles of base. So if you remember that moles is C times V, so then what we're looking for is the moles of acid. When are they equal to the moles of base? So CAVA equals CBVB. But the big thing with this formula is you need to be careful of the number of hydrogens in the acid versus the number of hydroxides in the base. Sorry, I forgot, in the base. Okay, so that's where we have to be careful of Stoich. Okay, so let's just do some examples. It's probably easiest. So we have 13, and again, so similar to C1V1 equals C2V2, then you just have to plug the numbers in and then look at what you have and what you don't have. So this is a little bit easier because A is for acid and B is for base. Okay, so for example here, 13.84 milliliters of hydrochloric acid. That means that the volume of the acid is 13.84 milliliters. Just neutralizes 25 milliliters of sodium hydroxide. So that is the volume of the base. Okay, and then concentration of the acid, that's what we're looking for. What is the concentration of the acid? And then the concentration, concentration of the base is 0.10 moles per liter. Okay, so the only extra step with this, when you have an acid, it has the hydrogens and the base has the hydroxides. So you need to count in the formula how many hydrogens there are and how many hydroxides there are. And actually, in this section, even if we were in school, I would give you the formula, and so does your textbook. Okay, so there is 1 hydrogen in hydrochloric acid, and there is 1 hydroxide in the base. So really, that once they're equal. So even if they were 1,000,000, doesn't matter. Once they're equal, whoa, sorry, that's not what I wanted. Then that's balanced out. So you don't have to worry about stoic. So this example is the simplest kind. The next example will look at what happens, what do you have to do when you have when they're not balanced, okay? So we change these into liters. And then similar to C1V1 equals C2V2, you can decide if you want to rearrange the formula first or multiply and then solve. It's up to you. So 0.1 times 0.025 is 0.025. And then the liters cancel. And then you're going to divide by the volume of the acid to isolate the Ca. And then just round. 0.18 moles per liter. Okay, so now in this question, now we've got H2SO4. So here you can see there are 2 hydrogens, and that's going to influence how we handle that, okay? How we handle the stoic. So what volume of, so this time we're looking for the volume of the acid. Its concentration is 0.45 moles per liter. And again, if you forget that this is sulfuric acid here, then again, look for the hydrogen makes an acid. And we're only dealing with strong bases or arrhenius bases this year. So this is a base when you see hydroxide, okay? And then number of hydrogens. Oops. This time we have 2. The volume of the base is 15. And the concentration of the base is 0.6. And the number of OHs is 1. So now that doesn't match. Okay, so the easiest, you can certainly do this full out. You can do stoic ratio. But if you use this formula, then, and you need to remember, like, A is for acid, right, which goes with hydrogens. Then what you're going to do is put the 2 out front there. So if you want, then, I mean, when you multiply by 1, that doesn't change anything, right? But the OH goes with the base. So you can always put the 1 if you want, but multiplying by 1 doesn't change anything. However, if you want to keep it all the same, then that's fine. So now we've got 2 times 0.45 and 1, and again, that's not going to change anything, but if it helps, then let's just leave it. Okay, so now we do need to multiply by that 2. Sorry, I don't know why I wrote a bracket there. Liters cancel. So then 1 times 0.6 times 0.015 is 0.009. And then to get the volume of the acid, now the moles cancel and you're left with liters, which is what you want for volume. If this is just a paper and pencil task, unless it says to change it into milliliters, you can leave your final answer like that, or you can multiply by 1,000 if liters bugs you. If we were in the lab, you would have to, because our graduated cylinders don't measure liters, but certainly with a paper and pencil task, that's fine. Okay, and then the last example is data. Basically, this is what we would have done in a lab. Okay, so a burette is weird because burettes, I don't know if you've ever seen them in the lab, but they're really, really long. So this is a cut up picture, but this would be the top and this is the bottom. So the top, if you can see that, is actually 0 and the bottom is actually 50. So what happens is in a lab, you would fill it up, pretend like this is clear, and you would fill it up to the top here, and it would look, you'd be like, oh, I want to write in my initial volume 0, but 50, because there's 50 milliliters of solution, but you actually write down 0. So a burette is set up to help you to not have to do a million subtraction. So this one says the initial volume is 0.1 of a milliliter. So let's say like right here, okay? And then the final volume is 12, so that says 7, so 12 would be down here. So then that's where the solution ends. So what happens is you've added the difference between them. So, and then when you start the second trial, now your second volume is actually 12.52. So you don't always go back up to the top every single time. So the burette is really set up to help you. You don't care where it starts and where it ends. You want to find the difference between them. And how would you know where to stop? Like, when do we decide what the final volume is? That's where you would do the procedure and see where you got visually, where you got equivalence point. So a titration is completed using a 10 milliliter sample of hydrochloric acid and a solution of 0.1 mole per liter solution of sodium hydroxide. The following chart, we always do 3 trials and take an average for titrations because it is a visual determination of when neutralization occurs. So we're going to calculate the volume of base added for each trial. So the base is in the burette and the acid, this is the bottom here, right? So the acid would be in the little flask and there would be some kind of indicator in there. So again, I like bromothiamyl blue. It is yellow. in a acid and blue in a base. So then when you get to neutral, then it's a clear, like the middle of yellow and blue is green, right? So students would often, they're very competitive about trying to get a very close to green color as possible. So again, you're visually determining, oh, okay, I'm going to stop my experiment. So then doing 3 trials helps to minimize error. So when we find the volume of base added, then hopefully they're pretty close together. So again, you do final minus initial. And actually, it doesn't really matter if you do it the other way, but if you get a negative number, then that doesn't make sense. You can't have negative milliliters, right? So calculate the volume of base each added. You're just subtracting. Subtract final minus initial. Okay, so now you can see here the final volume has now become the initial volume in trial number 2, but you still do the same thing, final minus initial, this time 12.46, that's pretty close. And then again, now this final has become the new initial, 12.52, all pretty close. Okay, so that was question A. B, calculate the average, sorry. So you just add them up. I don't know why I wrote this weird. So it should be around, like if you got 13.5, then that's weird, right? So you would know, you can kind of check your answer. Sorry, I don't know why I wrote the unknown on the right-hand side there, but that's fine. Okay, so use the average, calculate the unknown concentration of acid. So right away, we're looking for the concentration of the acid. The volume of the acid was 10 milliliters. And it's hydrochloric acid with 1H. And then the concentration of the base is 0.1 and the volume of the base. So now you use your average. But they're 1-to-1, so this time I'll just write it in. Oops. But it doesn't matter. But you can do that every time. So just remember, A stands for acid, B stands for base. So 0.1 times 0.01247 gives you 0.001247 moles divided by 0.010 liters. Then we're going to write 2 equations on the same line. Sorry about that. 0.1247 moles per liter. So it makes sense. It took a little bit more base to neutralize the acid. So if it was the exact same, then it should have been closer to 10 milliliters. But 0.1247 is not that much higher than 0.1. So the 12 milliliters versus the 10 milliliters makes sense. So there's not that many questions to try this, so give them a try. They're one of the 3 types. Either the moles of acid and base are equal, then that's easy, or you have to do stoic like the second one, or you have to find the volume of added first if it's a titration question. Okay, thank you.